Hello boys and girls, welcome to another episode of FoulkesBrau. Today is the 31st of January 2020, last day of the year 2020. Anyway, today I thought we'd shoot something fun, something interesting. We'd actually make something from scratch. It's a little project for a work colleague. The solution is very simple, but we can actually learn a bit together. I'll show you the easy way to do it, and then we'll learn a little bit about transistors, one of the basic building blocks of electronics, and hopefully you'll learn something and get to see how easy this thing is to use as a switch, and how it really is one of the basic building blocks of modern day electronics, especially since every IC that you buy, or integrated circuit, every chip will have a lot of transistors inside. Anyway, let's jump on the bench, let's have a look at the problem, and let's build something. Right, so here we are on the bench, and the problem that we have is this LED. So what we have is one of my electrical colleagues is building a test jig, and he's using the point of this test jig is to test a whole bunch of MV protection relays, medium voltage protection relays. So medium voltage in South Africa is 11,000 volts up, 11 kV up. I think they actually include 3.3 kV as well. So obviously when testing these relays, he's got certain issues where he's blowing fuses, so he is looking for a blown fuse indicator, except he's doing it arse about face, he's doing it the other way. So he wants the LED to be on when the fuse is healthy. Now this would be a very simple circuit. So these LEDs are 12 volt powered. If we have a look at it, I'll just open it for you. You can see there's our 4 LEDs. In there's a little full wave bridge rectifier, because this thing can be powered with 12 volt AC or 12 volt DC, and you can't really see the rating. It's rated at 20 milliamp, so you can't really see in those little vents there are current limiting resistors already in. It's a very interesting little thing. So to solve this problem rather simply, all we had to do, normally you would have a terminal strip that looks like this, and that's got a through wire in there, and then there's another part that's built on here that would have your LED built in, and that little LED would have a resistor. So all that would happen is if the fuse blew, in other words the fuse is sitting in here, if the fuse blew, the current would pass through there and the LED would come on. Now he wants it to work the other way, so if we do a circuit, it's easy enough. He would have his fuse, and all we had to do would come through this LED device of his. I'm going to draw the internal resistor. We'll just draw that around that so we know it's 1, and go to ground. If the fuse is healthy, the LED is powered. The LED will only draw what it needs, and as long as that's 24 volt DC or AC, that's fine. Problem solved. But that's too easy. So let's design something. Let's play with a nice electronic device called a transistor. Oh, so I'm having a beer. South Africa, we are back in lockdown level 3. So our family meeting outcome the other night no booze in restaurants, no bottle stores open, no blah blah blah, and everybody must be in bed sleeping by 9 o'clock tonight. Otherwise the police are coming for you. But anyway, let's see if we can do something like this with a transistor, and we'll do a little bit of maths with the transistor. It's very simple. I'm going to give you very simplified calculations that will get you in the ballpark and how to use them, and when you see how they work, you'll ask yourself why you're not using them. Very simple devices. So let's do that. Right, so first things first, we need our device we want to power. So I'm just going to draw our LED here. Again, we'll put in our current limiting resistors. I'm not going to put in the full wave rectifier, and we'll draw a block around it because we want to know that it's in one package, one device, and we know that's going to go to ground. Here we'll have our 24 volts coming in, or 12 volts in this case. So we're just going to put that there, the terminal. We'll put it 12. Do we need to mark it? Doesn't matter, it's 12. It can be AC, DC, doesn't matter. No, let's mark it VDC. So now we need a device that if there's a voltage here, will switch through to there. Now we could use a relay, electromechanical device, but they wear with time, and transistors are so cheap. We know this needs 12 volt. We know it's limited to 20 milliamp. Really, do you want to buy a relay for that? No. We could use a common garden variety transistor. Let's see, I've got something like that here, like this little device here. Let's see if we can zoom in for you. This FoulkesBrau has changed again, so now it's trying to figure out where they've put everything. Okay, it doesn't matter, I will just bring it closer. So here's a little common garden variety transistor, little package there, and this just happens to be a 2N3904 transistor, very common NPN transistor. NPN means it's made of two negative and one positive materials. Without going into too much detail, all it means is they've used a silicon substrate, and I think it's either boron or phosphorus, depending if it's PNP or NPN, to either create holes or electrons in there. And we'll show you a bit in the circuit detail now how that is going to work. So we're going to use this device. You can see it's got 3 legs. On this particular transistor BJT, in other words bijunction transistor, what you can see, the front side facing us is flat, and then it's half moon or half circle. So if you hold the flat side up on this particular transistor, the important pins, well, all 3 of them important. The middle pin is the base, what we're going to use to switch it on. The top leftmost pin is the collector, and the bottommost pin is the emitter. So very simply, we can use this device to switch this on. So I'm just going to move over a little bit. We're going to keep that there. Now what I want you to note is how I'm going to draw the circuit. I'm going to draw our transistor here. And this is a symbol. You'll see this little arrow is pointing out. I'm going to come to ground, and we're going to go up. I'm just going to draw our LED because we know it's got a resistor in, and that's going to come to our 12-volt rail. We can draw the LED, the resistor in, it doesn't matter, just for completeness. There we go. So that's our diode or LED. Q for transistor, and there's one leg missing here. Now if we look at that symbol, we notice it's pointing out. So the symbol for that transistor, or the NPN transistor, the emitter is pointing out. So in other words, never point in. Nice mnemonic to remember it. What you'll notice there is I've got the collector connected to ground, and the load is sitting on the emitter. I'm doing that for a reason, and you'll see very shortly. The nice thing about transistors is we can use a very small signal here on the base to switch a very large signal here on the emitter. So I can use a small voltage and current here to switch a larger voltage and current here. In our case, we're using it as a switch on and off, but we can use it as an amplifier. In other words, we can use a very small signal here to drive a very big signal here. We will do some stuff with that. I just wanted to show you how easy these are to use as a switch, and that the maths is really not that scary. So if we look at this transistor, we have a few values in the data sheet. You can download a data sheet for it. There's nothing really amazing to it. We know we want to use this as a switch, so we're going to use rule of thumbs. We have a thing called HFE in the data sheet, and the thing with the HFE is it's called the DC gain, small signal gain. What it means is if I put X amount of current, remember the transistor is current driven, if I put X amount of current into here, it will be multiplied by that small signal gain on that side. So let's do a little bit of a quick calculation. We know that this LED is 12 volts. We've got a 12 volt supply. We know that we'll have a volt drop across the collector emitter saturation voltage. I'm not worried too much about it. That's the beauty of a transistor. The saturation voltage across here and here is so little, where MOSFET has a parameter called RDS on. So as the voltage goes up, the current flow goes up, so that voltage drop will increase, where transistor has a fixed voltage drop, which is nice. Anyway, we know we have 12 volts. We know we need 20 milliamp. Now if we go and look at the data sheet for this 2N3904, we'll just put it in here. We have a few values and graphs to look at, so I'm not going to show you the data sheet. You can look at it out of yourself, out of your own, in your own time. And we're not going to look at it because we're going to use general engineering principles here. So anyway, this gain varies from 30 to 400, and it will vary depending on what voltage we've got here versus what voltage we got here versus what voltage we got here, and. So if we're going to use a transistor as a switch, a generic rule of thumb is you can make the gain 10. So before this clip gets too long, let's just start a new one. Okay, so of course, if you want to be more precise, what you can do is take, depending on what your transistors got in its parameters, you can always take the lowest small signal gain value or beta value. In general, when we're designing, if you're using the transistor as a switch, use a gain of 10. Trust me, the lowest value in the data sheet is very unlikely to be smaller than that. So we are guaranteed to switch it on. What we're trying to do, we're not using it as an amplifier. We want to switch it on, and we want to switch it on hard or into saturation, as it's called. So if we know we've got a gain of 10 and we want 20 milliamps, how much current do we need here? Well, that's easy. Divide that 20 milliamp by 10, divided by the gain. So here we need 2 milliamp. Don't even need a calculator. You understand how I got there? Our load is driving 20 milliamp, or we're driving a 20 milliamp load. We're working on a gain of 10. The transistor is an amplifier as a switch, so we use a smaller current to switch a larger current. Divide the large current by the gain of 10 that we said we'll use as a generic engineering factor, and we end up with 2 milliamp. Rather simple. But we've got one last thing to take care of. So we know our transistor is a current-driven device. So not only do we use a smaller current to switch this bigger one on, we also use a smaller voltage. Now we have to do a little bit of maths. And it's really not that difficult. So what I'm going to do, because I've only got one supply, I'm just going to put a resistor here. And we'll take it to our 12 volt rail. Earlier on I told you we connect the NPN transmitter to the ground or 0 volt, okay? Because not only do I need a bit of current, I need a voltage drop between this base and the emitter, between here and here, to switch the transistor on. In other words, this base voltage must be X times higher than that voltage to switch the transistor on. And that is one of the primary reasons why we put the load up here on a NPN transistor. The PNP is the other way around. We're not going to talk about it. Everything about PNP is just the opposite or inverse of what I'm saying here. So by knowing what our reference is here, our 0 volt, well, that's easy enough to just bring this voltage up by whatever that difference must be. Now, typically, rule of thumb, you can work anywhere from, you can go look in the data sheet, it will be given to you as VBE, voltage base emitter saturation. So we can just write here VBE sat. On these small power transistors, small signal transistors, that would be 0.8. In the old days when I was studying, it was 0.7. You can work with 0.8. 0.7 is just because of the materials that it was made with, but we're not going to go into that. So now we need to find this resistance value. Well, that's not difficult at all, because we know what voltage we need here, so we do a simple calculation. A bit of Ohm's law. So we've got 12 volt there, we need 0.8 there. So R equals V over I. You should remember this from standard 6 physics, I think. 12 minus the 0.8 over 2 milliamp. And if we go and do the maths, that's pretty easy. Let's see if you can see the calculator. 12 minus 8 divided by, I'm going to do this, 2 exponent minus 3. I work in engineering notation. saying that is the same as saying 0.002. Okay, it just makes it easier. What have I done? 12 minus 0.8 divided by 0.002, and you see it gives me 5.6 to the power of positive 3, or 5,600, or 5K6. So we know that this is a standard resistance value, so I can put a 5K6 value resistor in there. Of course, our fuse is here. As long as the fuse is healthy, the base will switch on, the transistor will conduct, and we will power the LED through here. If the fuse blows, well, the whole circuit's dead. It doesn't matter whether we had a base or not. If the fuse blows, everything's dead. So yes, we didn't need the transistor to do it. It just made for a nice little problem. Of course, we've got a few things left to calculate it. We need to calculate the power through our resistor and our transistor to make sure they're not going to blow. I'm not going to do that. I'm sure you can do it. What I can tell you, this will have typically, the transistor will typically have between the collector and emitter, it's roughly about 0.8, 0.9 volts drop saturation. So that means you've only got 11 volts for the LED diode, but that's easy enough if you've got a 1 volt drop here and you've got 20 milliamp. Well, then you're only passing 20 milliwatt through the transistor. The transistor can handle way more. I think it can handle 200 milliwatts, so that's more than fine for our transistor. If we do, okay, so I'll just put the formula here. So for there, that we'll call it PQ. It's voltage through Q times I through Q. Okay, so we said it was a 1 volt times 20 milliamp, so we'll have 20 milliwatt. The other formula we could use here, we could use P equals I squared R, or we could do the other route, but I'll give you the other formula. I squared R equals 0.02 squared times 5,600, and that's going to give us what? I squared so small, another 22 milliwatts. So we're really not using a lot of current and power in this circuit. So let's get a breadboard out and let's build this and let's see if it works. Right, so here on the bench we have a breadboard. Everyone playing with electronics should have one of these. It's a very nice device for prototyping things. All I have here is my power supply coming in, my bench power supply. This is some of the circuit we were testing with a MC33063 switcher. When I the solar powered cell phone charger. Anyway, components, again we have our transistor, and we have a 5K6 resistor. So really not much to this. Let's put the components in. The way it works, running vertically in your case, this way, down to up, whatever. These lines on each break is one circuit piece. I'll try and show you that better. Running like that is one circuit strip, but running horizontally they are isolated. And then obviously the red and the blue are power strips that run all the way down. So let's put our transistor in here at the bottom, one leg in each hole. You should be able to see that. Yes, I think you can. So what we want to do, if we look at our circuit, let me just, if we can remember it, up there, we're going to come from our power rail through a resistor to the base, so through a power rail, through our LED to the collector of the transistor. I keep wanting to say transmitter. It's not a good day. So what I'm going to do is I'm going to put the resistor from the power rail up here somewhere into a line, and I'm going to take one of these jumper wires that I've got. I'm just using these Arduino things. I'm going to take the, let's move our board up rather like that, the emitter. Remember I said that is the third leg. So I'm going to take the emitter leg down to ground, which is our blue line there. So let's see. What I'm going to do here on the side, I'm just going to switch my multimeter on. Let's see if I can put it somewhere where you can see it. To resistance. And we're going to measure between, I'm measuring the two leads. We'll measure between the collector and the emitter, and it's open. So what happens if I take this resistor to our base, the third leg up there, and we go back and we measure the same thing. Oh, we have a very different reading. I did plug it in the base, yes. Okay, so our transistor is now switched on. I'm going to switch. Let's just put that on as well. It didn't switch on properly, but it did switch on. So I'm going to go again, collector to emitter, and you can see it's now 11 ohms. If I take the base out, then the transistor is, to all intents and purposes, off. We'll put voltage on the and current on the base again. $11 ohms. See if I can hold it there. No, I can't with one hand. Sorry. 11 ohms, and open. So what else would be interesting to show you? Maybe the base to emitter voltage. Let's see if I can put it there. .754 volts DC. I've just got the leads reversed, so that 0.8 that we worked with, close enough. Very good. So one last thing to do is to connect up our LED. So let me just put 2 leads into it. I must say it's been rather quiet this side because our clowns in charge have closed everything. So I believe a lot of people are stuck at the coast with not being able to go to the beach and that sort of snot. Okay, we're going to take our base out. I'm going to zoom out a little bit. Come on, zoom. I want to zoom out. Like that, I think. So what I'm going to do, here I've connected 2 leads. I'm just going to connect the 1 lead, like we saw in our circuit, to the collector. That's that rail. The other lead will go to the positive rail. And you can see it's all off. And if we go and put our base in, let's see if you can see it. There, they switch on. Let me try and get my hand around it like that. A bit darker so you can see a bit better. And we'll do it again. There you can see. As soon as I put the base leg in, our transistor switches on. So there you go, using a very small voltage and a very small current to switch a larger voltage and a larger current. So I hope you found that interesting. Transistors are not that difficult. Very easy to use. There's not major maths involved, especially if you only want to use it as a switch. But very versatile devices. We can do a lot of things with transistors. So let's set up for the closing shot. So there you have it, boys and girls. There's really not much to it when using BJTs or bijunction transistors as switches. Very simple. Current driven device, you need voltage. Using a small current, small voltage to drive larger currents and larger voltages. Maths is very simple. Drive the transistor into saturation, you will switch it on. MOSFETs, on the other hand, are a little bit different. If there is interest, we'll do some more circuits with transistors, not just the switches. We'll do some circuits as amplifiers, analog stuff. Very interesting. A little bit more maths, not too much, as long as you keep your head around you. Anyway, I hope the coming year is better for you people than what this one has been. I hope you have a safe, healthy, blessed new year. We'll catch you in the next one. Cheers.